Hello, my name is Carrol Lay, and today I'm gonna explain my final assignment of calculus. Okay, let's get started. First, here's the first question. So the first question is, so I'm gonna read it first. So due to a storm, air traffic control instruction, a pilot flying at the altitude 4 miles to make 90-degree horizontal turn while climbing to 4.2 miles the path of the plane during the maneuver modeled by RT this formula. Okay, and where's the t is time in hours and all distance in miles. So here we're gonna find first the speed of the plane during the maneuver, and we need to compute also the tangential and normal components of the acceleration AR, AT, and AN, which is one is 0 and y is 0. Okay, let's get started. So here's A. Here we need to find the speed of the plane. So here we're gonna use the velocity. So the velocity is the derivation for this value. So here first we're gonna derive the VT, the velocity. So here's the value. In here, for each of the inside, we're gonna use chain rule to solve it. That's why this value from 10 cos 10 pi t, we got negative 100 sine 10 pi t, and for 10 sine 10 pi t, we got 100 pi cos 10 pi t. And since 4 is a constant, it will be gone, and 0.2 t, it will become 0.2. Okay, after this we're gonna find the, so here we're gonna count the velocity at the highest point. That's why we calculate this unit. So here we use here's the formula of this, root of minus 100 pi sine 10 pi t square plus 100 pi cos 10 pi t square plus 0.2 square. So after the calculation, here's what we got. So the velocity of the plane is 314.2 miles per hour. So this is the velocity of the plane. So here we're gonna continue to section B, which is we're gonna compute the tangential and the normal component of the acceleration. So acceleration we're gonna declare as AT. So we know that acceleration is a derivation of the velocity itself. So here we're gonna derive again the velocity, and we got this. After we got it, we gonna find the AT. Since we know AT is the value of VT, this VT, then we already got here is 314.2 miles per hour. As we already know that is a constant, so when you derive it, it will be 0. So here we know that AT is 0. So the AT is 0. So here we also know that because that is a constant, that's why like the AT is 0. And now we're gonna find the magnitude. The magnitude is acceleration t. So here's the formula. So here we're gonna count root square of this value. And after we got it, this is the formula of AN. Because AN needs to be, so here's the formula of AN, and we already found this for this value, and we amplified it in here. And since we know the AT is 0, then it's gonna be 0 square. After that, we're gonna use the pi square and turn it to 9.86, and we timed it together, and we got this 9,869.6. So here's the final value of the calculation, or the final result. Okay, now we're heading to the second one. The second question is, a car travel along the curve of y equal to 1.3 x cubed, where both x and y are measured in miles. The maximum safe speed on a curved path is inversely proportional to the square root of the curvature at the point. So first we're gonna find if a car safely travel 30 miles per hour at the point 1 and 1.3, how fast can it safely travel at the point of 3.3/2 and 9/8? And interpret the geometric significance of the curve in the term of road safety. Okay, so here we're gonna start. So here we're gonna declare it to be kx. Kx, this is the formula that we're gonna use. So first we're gonna find the first and the second derivative, because in his formula it's gonna look for the second derivative of the function. So here we got x squared, and after this we gonna get the second derivation is gonna be 2x. So after we got it, we're gonna amplify it into this formula and we're gonna start to do the calculation. So after the calculation we will get this value. Now after we got it, we're gonna check the value from the point of 1 and 1.3. So here when the x is 1, we will get 1/2 root of 2, and when the x is 3.2, we will get the value of 81/61. So here we also gonna see we're gonna try when the x is 3.2. So here we're gonna amplify, put this formula of this into this, and we got 192 over root of 97 cubed. So after this we're gonna find the geometric certificate curvature term road safety. So we know that v1 over v2 is equal to root of k2 over k1. So here we already get so here we know that k1, this is k1, so k2 and k1. So after this we're gonna implement it here. So times square of 2, this one. So as we know, like v1 is over v2 is equal to k2 over k1. As we know, so we start to calculate. So 30, we know that v1 is 30. So here we're gonna put it, implement it. So 30 over v2 is equal to 9.2, this value, and times, since we know that it's 1/2, so it's the same as we count it as times root of square or root of 2. So after the calculation we will get this value. So here's gonna be the final result of the problem. Okay, now we're going to the next problem. So here the problem is the temperature in Celsius at the point of x and y on the metal plate is given by the function. So Txy is equal to 400 exponent times minus x squared plus y over 2, this formula, and the x is greater or equal to 0 and y is greater and equal than 0, so there is not gonna be a negative value. So here the first problem here, we need to find the gradient of this value, and the second one we need to find the unit direction from the point 3.5, which is the temperature remains constant. So here we know that the gradient, to find the gradient we need to find the fx and the fy first. So here's when we derivate this function into the respect to the x, and here we're using the chain rule method to calculate this formula. So here's gonna be the final value of the fx, and oh sorry, this one, and it's also will be the same as for dot t fy, or derivation with respect to the y. Here we also use the same method, is chain rule, to calculate these values, and here's the value that we got. And as we know, so this is the gradient that we already calculated, so this is gonna be the gradient. So here we also gonna implement the gradient at the point of 3 and 5. So here we put the x is gonna be 3 and the y is gonna be 5, and here's what we got of the gradient. And now we calculate this value into the highest point, like the highest point, which is also like which the temperature remains constant. Here we're gonna use this method again, and after that we will get this value. And after we have it, we can now find the unit direction of the vector. So the result of the direction of the temperature change at 3 and 5 is 2 over root of 188 and negative 12 over root of 148. Okay, now we're heading to the last problem. So the last problem, I'm gonna first read it first. So a candle manufacturing company produced the candle to location. The cost function in dollars for producing x1 unit at the location in x2 unit location are given by with this formula. Each candle sell for the price of the total profit. So here's gonna be the profit. So here we're gonna find the first problem. We're gonna find the value of x1 and xy that maximize the profit, and b we're gonna interpret result in term in many units which locations will be produced. So here we're gonna start the calculation. So first we're gonna use this formula, because this is gonna be the price. So first we're gonna count the price first, and first we're gonna simplify this formula. So here's the simplification of this formula, as you can see here. After we simplify, we're gonna derivate it respect to the x and respect to the y. So after we derivate it, this is gonna be the value. And here we're gonna find the critical point of the value, and we got the x1, we got 275, and the x2 is 110. So that's mean the company needs to produce so the company to get the maximum profit, the company needs to produce 275 unit at the location 1 and 110 unit at the location 2. Okay, I think that's all for my explanation. Thank you for your attention.